Hello, everyone. What I want to do now is talk about an interpolation theorem that is very similar to the Riesz-Thoren interpolation theorem, but in practice is quite a bit different in terms of what you can assume, what you need to assume to invoke the theorem. And it's equally as important as the Riesz-Thoren theorem. And this is called the Marcinkeiwicz interpolation theorem. Okay, and the very beginning of this is the following very easy homework. So let's say M is Lebesgue measure. Let's say F is a measurable function on Rn. So in that case, we know that this set here is measurable. And I like to use script M for measurable subsets of Rn. Okay, so a very slight variation of Chebyshev's inequality says for any q positive, the measure of this set here is less than or equal to the LQ norm raised to the q over lambda to the q, and the proof is basically the same as the proof of Chebyshev's inequality. And you've definitely done this in 510A. It's a very straightforward problem. I would probably first, if you forgot how to prove this, I would first just start off with this here, which is obviously just this quantity here. This is bigger or equal to, well, you know, I might just make this as a homework, but it should be pretty clear how to go from here through a few easy steps to lambda to the q times this quantity here. Okay. So this almost trivial one-line result leads to a very important definition, particularly for us. And that is, if we have a bounded operator, not even necessarily linear, but let's say it's just bounded. Let's say let's assume for now it's linear. If we have a bounded linear map from LP to LQ, then this measure here is less than or equal to this quantity here. That's exactly what we just had a second ago. Instead of F, it's TF. But if T is bounded, then this is less than or equal to, well, TF LQ, assuming it's bounded, less than or equal to the operator norm to the Q, F to the LP to the Q. Okay? So here, C is going to be just the operator norm T, LP to LQ. Okay? Now, so if T is bounded, then this is true. Okay? Now we say that if T is some operator, not necessarily linear, but if T is just some operator taking LP and spitting out measurable functions, so maybe M is not the best letter. Let's let me just say instead is measurable. So let me reserve script M for measurable functions on Rn. So if we have some T takes LP and spits out measurable functions, we say that T is weak type PQ if this is true, meaning that if there exists some C where the following is true. And the following is this. If there exists some C where for all F and LP this is true, then we say T is weak type. So in particular, if we have T is bounded from LP to LQ, then T is weak type. That's exactly what we have here. So this is a weaker version of boundedness. And we're not just doing this because it looks cool or it's just funky looking or whatever silly reason you might think we're doing it for, there's a lot of operators, in particular the Hilbert transform, where it's just much easier to prove initially its weak type. In particular, we'll prove that the Hilbert transform is weak type 1, 1. And then try and use that to prove LP boundedness of your operator. But it's a very good starting point often for proving boundedness of an operator that you want, ordinary boundedness. And I should say in the literature often when an operator kind of T being bounded from LP to LQ, that's often called strong PQ type. Strong meaning just usual operator norm LP to LQ. Okay, so another easy homework that certainly was a prelim problem. Actually, it's quite often a prelim problem. I've probably written it up into, I've probably put it into 2 or 3 real analysis prelims. And it wasn't just a silly little, let's just test you to see if you know how to use Fubini's theorem. An extremely important yet easy homework is the following result. Okay, and this actually connects ordinary, LP boundedness, operator norm boundedness of operators to weak type inequalities. And this is the ordinary LQ norm raised to the Q, or just this integral here, can be written as this funky integral Q times 0 to infinity lambda to the Q minus 1 times the measure of this set here. And here we're assuming obviously F is measurable. Okay. And sorry, there should be a d lambda here. Okay. So oftentimes in various textbooks, this is called the distribution function, basically because it is basically the same thing as a distribution function in probability theory when you have a probability distribution function for your random variable. We're not going to do connections to probability here, but I mean, yeah, this is basically a distribution function in probability, so why not call it a distribution function for what we're doing? Okay, and D is for distribution, subscript F is just F. And this is kind of looks a little funky, but it's really lambda, so this really should be df of lambda. Sorry about that. And it's this whole thing here, this whole measure is the distribution function here. So it's really q 0 to infinity lambda to the q minus 1 df lambda d lambda. Okay. Okay, so we need another definition, and that is a sublinear map. So let's say M prime is a subset of measurable functions that just happens to be a vector space. Okay, so T taking in M prime, spitting out measurable functions is sublinear if the following two are true. It's not quite linear, but it's basically, and often just as good as linear. So T applied to two functions, plug in X, is less than or equal to, well, absolute value of TF of X plus absolute value of TF0 of X plus absolute value of TF1 of X. And we can basically pull constants out, except we need absolute values here. So, the absolutely simplest example of a sublinear operator, I mean, this is a fairly trivial example, but basically the idea is we want operators that behave like absolute value in some ways. So this is sublinear. And here M prime could be just measurable functions themselves. In practice, you often want to, you don't want to just look at measurable functions. You want to restrict yourself because oftentimes operators aren't really defined on all of measurable functions. We'll talk about another very important sublinear operator in the next video, which is called the Hardy-Littlewood maximal function, and we will prove the Lebesgue differentiation theorem, which is really cool. It's basically a result saying what is true for Calc 1 integration. Basically, I forget, it's the second or first fundamental theorem of calculus, is actually true for L1 functions. Okay, so the Marcinkeiwicz interpolation theorem is as follows. Let's say we have P0 less than P1, and P1 being possibly infinity and P0 being possibly 1 is quite important. And let's say we have a sublinear map from LP0 to LP1, LP0 plus LP1 to M. So this map takes in functions of the form G plus H, where G is in LP0 and H is in LP1, and spits out measurable functions. If T is weak type P0, P0, and weak type P1, P1, then for any P between P0 and P1, we have the following strong type, basically the following operator norm type estimate. Okay? So in particular, what we will do for the Hilbert transform is we will prove a weak type 1-1 bound. Okay? So that means that we will have in this Marcinkeiwicz interpolation theorem, we will have this equals 1. Well, we know that the Hilbert transform is weak type 2-2 because it's an isometry on L2. Okay, so that would immediately give us, as a direct and very important application, that would give us that the Hilbert transform is basically bounded from on LP rather for all P between 1 and 2. And fiddling around with duality, it's easily shown that if you have that, then you actually get you get boundedness on LP for P bigger than 2. Okay, so yeah, that's exactly how we will use the Marcinkeiwicz interpolation theorem for the Hilbert transform. It's a little bit more subtle than that, but not a whole hell of a lot more. Because if you remember, we only have a nice integral operator representation of the Hilbert transform for Schwartz functions. But anyway, another thing is you'll notice that, well, I should say C0 and C1, what are they? Well, C0 is really the infimum of all C's where this is true, and here Q is P0. We know such a C not infinity exists because T is weak type P0, P0. So just take the infimum of all these C's, and that is what C0 is. And analogously, C1 is the infimum of all these C's, where Q is, Q and P rather are P1. Okay? Yeah, and sorry, C0 is the infimum of all these C's, where Q and P are P0. Okay? So such a C exists for Q and P being P1, so it makes sense to take the infimum of all these C's. Okay? And it's the infimum of all the C's that work for all F and LP0, respectively, LP1. Okay? So it's basically like a weak type operator norm, essentially. Okay? And so you'll notice that this is the same bounds we get in the Ries-Thoren theorem, where C0 and C1 are basically the operator norms corresponding to your two different bounds. So the big difference between the Ries-Thoren theorem and, well, actually, I'll talk about that at the end. Yeah. So one thing to notice is that when P gets close to either P0 or P1, these bounds blow up, and that's just the nature of the Marcinkeiwicz interpolation theorem. That's the sacrifice we make for only having to acquire weak type bounds to prove strong type bounds, which is usually what we want. For example, we want LP boundedness of the Hilbert transform. Okay, so what's the proof? Well, first, P1 equals infinity, which is an important case. We'll apply that case to the Hardy-Littlewood maximal function. There we'll prove that this is weak type 1,1, and it's fairly trivially strong type infinity, infinity, and hence weak type infinity, infinity. And I should mention, you do have to modify this definition a tiny bit when particularly Q is infinity, but that's, I mean, that's not particularly too, well, actually, I should say, yeah, when Q is, I'll make a comment on that in the homework. Yeah, I'll make a comment on that in the homework. What does it mean to be weak type P infinity? But anyway, it's actually just, it's really just strong type. Okay. Right, so let's look at P1 is infinity, positive infinity, or less than positive infinity, rather, about that. So let's say F is an LP, and for C positive and lambda positive, we're going to decompose F in a very clever way. Lambda is just the lambda from writing the integral of modulus F of X to the P in terms of integrating the distribution function. C is a positive constant that we'll determine at the very end. But for any C positive and any lambda positive, I can write F in the following way. Either absolute value of F of X is less than C lambda, or it's bigger or equal to C lambda. So no subtlety there. And because F is an LP, you can check that F0 is an LP0 and F1 is an LP1. Okay, and just notice that because T is sublinear, TF of X in absolute value is less than or equal to TF of 0 in absolute value plus TF of 1 in absolute value. Okay. And you can use that to check almost trivially that if TF of X in absolute value is bigger than lambda, then either TF of 0 of X has to be bigger than lambda over 2 in absolute value, or TF1 of X in absolute value has to be bigger than lambda over 2, because if neither of them are true, then TF of X in absolute value is less than or equal to TF of 0 of X in absolute value plus TF1 of X in absolute value, and that's less than or equal to lambda over 2 plus lambda over 2 is lambda. So this is very trivial. Now what we do is just take Lebesgue measure of both sides. So that's less than or equal to, get rid of this here. Well, I'm taking the measure of the whole thing, so by subadditivity, that should be an M. Okay. Well, this is a distribution function for TF with lambda plugged in. This is the distribution function for TF0 with lambda over 2 plugged in. This is the distribution function for TF1 with lambda over 2 plugged in. So we get this almost trivial but important inequality relating the distribution function of TF to that of TF0 and TF1. Okay, so what I can do now is plug this in. So let's get rid of this here. Don't really need it anymore. We really just want what's circled. Okay, anyway. All right, so now let's use our connection, the connection between the LP norm to the P of TF and this integral here, integrating the distribution function. Okay, so we're going to plug this in. So we're going to take our inequality for the distribution function of TF and plug it in. So we're using this here. So we get these two. Okay, so now what we're going to do is use the weak type inequality bounds. Okay, the distribution function for TF1 plugged with lambda over 2 plugged in by the weak type, P1 type bounds. Well, it's really going to be dividing by lambda over 2 to the P1. Well, let's just flip it to bring it upstairs. So it's C1 to the P1, 2 over lambda to the P1 times this LP1 norm to the P1. Well, this is exactly the LP1 norm of F to the P1, except for this characteristic function here. Okay, because remember what F1 is. F1 is exactly the same thing as F, but times this characteristic function. And we get the same, basically the same estimate for the distribution function applied to TF0. So this is how we're going to use the weak P0 type bounds. Okay? And we don't just want to throw out these characteristic functions. They're extremely important when we use Fubini's theorem in a moment. So we plug these estimates. Right. So we plug this estimate and we plug this estimate here into star here, which is exactly this here, which is an estimate for what we're trying to get, the LP norm of TF to the P. And we get the following kind of ugly mess, but it's really not too bad. Okay. All right, so now what I want to do is a little bit of almost magical reasoning. It's really not magic. It might just look it. So this here is really, if you think about it, a function of x and lambda. In the sense that this characteristic function is 1 precisely when, for any x in Rn and lambda positive, f of x in absolute value is bigger or equal to c lambda. This is precisely 0 if for any x in Rn and lambda positive, f of x is less than c lambda in absolute value. Okay, not a very subtle observation here, but that means you can kind of think about this characteristic function here is going to be equal to, let's just rewrite it in a slightly different way. So it's x lambda. And I should write x in Rn, lambda is positive, but there's no way I could fit it here, so I won't. Okay, so it's still a function of these two variables. Well, a trivial way to rewrite this is just lambda is less than or equal to c over absolute value of f of x over c. So I can write this as lambda is in the interval f of x absolute value over c. 0 So it's bigger than 0 and less than or equal to absolute value of f of x over c. Okay, let's move this up and make this a little bigger. Okay, and likewise, this characteristic function here is the same thing. Well, it's really a function of x and lambda. So it's really x lambda. But more importantly, this is going to be, well, you should be able to figure this out. All x and Rn, lambda positive, where, well, lambda is bigger than f of x over c. And that's it. F of lambda is bigger than, sorry, this looks messy as all anything. Sorry about that. This. Right, so just divide by c. Lambda is bigger than f of x over c. Well, we're assuming f is an LP, so it's finite almost everywhere. So we're safe with, you know, f of x. Not worrying about f of x is infinity. So lambda, we're not considering infinity. Okay, so, or really just we're doing 0 to infinity. So yeah, whatever. All right, so let's plug this in and use Fubini's theorem. Actually, I should plug in x lambda. Okay. So just to make the point clear, I'm going to omit the dependence on x, though it's implicitly dependent on x. Okay. Okay. And I should mention here, when I plugged in, let's do just P0. When I plugged in for P0, I really wrote this as 2C0 raised to the P, lambda to the minus P0. So I took out the 2C0 to the P0, and here is the, this is the lambda to the minus P0. Okay, same thing for P1. Okay, right, so now here, one second. Right, so here, what effect does this have? Integrating this characteristic function for a fixed x, this means that we're going to cut off when lambda is bigger than f of x in absolute value over c. Same thing here, we're going to cut off this integral when lambda, well, the integral is 0. We're going to cut it off when lambda is less than or equal to f of x in absolute value over c. So this is just going to be 0 to f of x in absolute value over c. The second one is going to be f of x in absolute value over c to infinity. Okay, so now we can just do these inner integrals. It's just a calc 2 improper integral, really. And so in particular, you'll notice that this quantity here, let me go to red because I'm making a comment here. So this here is going to be certainly bigger than -1 because P is bigger than P0. So P minus P0 is bigger than 0. So I can integrate this, and there's no problem with integrating it and plugging in lambda is 0. Okay, so I do that. I get exactly Well, it's going to be lambda to the, just integrate, calc 1 integrations, lambda to the p minus p0, plug in f of x, an absolute value over c, plug in 0. Well, you get exactly, the 0 term is 0. Because again, p minus p0 is positive. So 0 to the p minus p0 is 0. So you get this term here. And then do the same thing. You'll notice that because p is less than p1, this here is less than minus 1, which is just what you need. So that when you take lambda to the p minus p1, that's less than 0. So plug in lambda's infinity, you get, you get 0. Okay. So when we do the calc 2 improper integral, because it's going to be, you plug in infinity, you get 0, then minus, it becomes p1 minus p instead of p minus p1. But otherwise, it's basically the same thing here. Okay, and we're almost done with the magic trick. You'll notice that, well, let's capture the p0 here. You have f of x, an absolute value to the p0, p minus p0. Well, that adds up an exponent to absolute value of f of x to the p. Same thing here, absolute value of f of x to the p. So we get the following equality. For, add these two up, we get the following. Okay, here I'm pulling out, well, this constant here, p 2c0 to the p0, p minus p0, little c to the p minus p0. Here I'm pulling out 2c1, p1, p1 minus p, little c to the p minus p1. Okay. Okay. Right, so what I want to do now is, so how do we still don't exactly have the constants we want. So this takes a little bit of elementary work. So what I first want to do is combine things. So I want to combine everything under a p0 for the first term. So it's 2c0 c to the p0. And in the bottom, I have a c to the p. Well, I also have, sorry, let me get rid of this here. I also have a c to the p in the bottom here. So I can pull out that c to the p, and c to the minus p1 in the bottom makes it a c to the p on top. Okay. So the next thing to do is, a good educated guess is to pick c where these two are equal and hope things work out. And that's exactly what we're going to do. So most textbooks from here just say, well, now it's easy, we're done. I'm actually going to go through the work because it's really not that quick. It takes a bit of work to go from picking C where this is true to getting the bounds we want. Okay, so if this is true, then I'm just going to write, I'm going to factor out a common 2c0c to the p0 because that's the same, this 2c0c p0 is the same thing as 2c1c p1. So this here is really equal to, well, it is 2c0c to the p0. Right. Okay, so, right, so now what we get is exactly this here, raising everything to the 1 over p. So it's p to the 1 over p, c, and in the bottom to the p to the 1 over p is c. Can't really do anything, just divide, take this P0 over P. This is going to be 1 over P. So these constants are at least exactly what we want. So let's just kind of put a check mark in the constants we want. This is basically what we want, this term here, and this term here. And obviously this is what we want. That's f to the LP of f. So we need to work on this term here a little bit. And actually, I didn't mention it. I really should have. But yeah, so here we're picking theta in the exact same way we picked theta for the Reese-Thorin theorem. I don't know why I didn't mention that, but. So here 1 over P is going to be theta over P0 plus 1 minus theta over P1. Sorry about that. I'll make a comment in the video. Anyway. Okay. Right. So let's use this and manipulate things a little bit. Okay. So first of all, what I could do, I want to solve for C, and I'm going to divide or take everything to the P1, so that gets rid of that. So I'm going to divide everything by 2C1. Well, that gets rid of that. Okay, so I have C is P0 2C0C to the P0 over P1, that exponent, divided by 2C1. Pretty trivial. Okay, so let's put this to good use. Okay, so that means that, right, so I'm going to take 2C0C to the P0 over P, divided by C. Okay, well, so C is this. So it's 2C0C to the minus P0 over P when I take 1 over C. So it's P0 over P, the exponent, minus P0 over P1. Well, if I divide by C, I get, it's, 2C to the minus 1 in the bottom. So that makes it 2C1 in the top. Okay, so absolutely trivially, we have this equality here. Well, you can check, and it's really genuinely very easy to do, that these two exponents are going to be the same. There's really not a whole lot to it. All you really do is multiply everything by P1 here. So P1, 1. This goes bye-bye. Okay. Or rather, sorry. Second. Yeah, sorry, you don't want to do that. What you want to do is multiply everything by P0. Sorry about that. So this goes away. And now you have P0 times this here. So you'll notice that you'll have a P0 over P1 term, which cancels this P0 over P1, because it's positive P0 over P1 when you distribute the P0 to this term here. And then you just simplify a bit, and you get this here. Okay. Okay. On the other hand, so we have, let's just manipulate our equality one more time up here. So let's get rid of this here. Give me a moment here. Okay. Right, so now what I want to do is just simply raise both sides to the 1 over P0. Or sorry, raise both sides. Yeah, sorry, I want to raise both sides to the 1 over P1. So that's the P0 over P1 in the numerator. So that gives us 2C1C is going to be 2C0C to the P0 over P1. Okay. Well, that's great because what I can do is I can then write C1 over C0 as 2C1C over 2C0C. Okay. Well, so right, so let's take, so just divide this by, right, so here I'm just dividing everything by 2C0C, divide this by 2C0C. Well, that just makes it a -1. Okay. Well, right, so what this is saying is, so just take 1 over everything. C0 over C1 is going to be 2C0C, 1 minus P0 over P1. So raise both sides to the theta. And we get, I'll write it exactly as we have it up here, with brackets and all. We have C0 over C1 to the theta is going to be this quantity right here. So let me get rid of this here. Give me a moment. Right. So this quantity, this whole thing here with this little manipulation that we did is going to be C1 over C0 to the theta. So this is star, star, star here. This is just simply 2C1 times, 1 second. Sorry. I don't know why I put it. C0 over C1 to the theta. I don't know why I put C1 over C0 to the theta. Sorry about that. A little silly error on my part. So it's C0. So I guess I theoretically could have left this as a homework, but I definitely thought this was a bit too much of a pain in the ass to do for homework. Okay, anyway, so this star, star, star quantity here, which is exactly what's here, is 2C1 C0 over C1 to the theta. There's no, we've eliminated little c here. So we don't even have to really solve for little c, though it's basically trivial algebra to do that. Star, star, star is 2C1 times this quantity here, which is just 2C0 to theta, C1 to the 1 minus theta. Okay? Well, that's really the only thing we needed to finish up, is we want a 2, and we want this kind of Riesz-Thoren-like quantity here. Okay? Which, remember, is exactly what's expected because we kind of did a trivial interpolation between two different LP spaces just using Holder's inequality. So if you have an interpolation result that you don't get this, it's weird. This is what you should always get for these kind of interpolation results. Okay, and that finishes the proof. Okay, what I finally want to talk about is comparing the Riesz-Thoren theorem to the Marcinkeiwicz interpolation theorem. And I forgot to mention, I'll make a comment in the YouTube comments section, that here theta between 0 and 1 is chosen in such a way that 1 over p is theta over p0 plus 1 minus theta p1. Okay. And right. So I mean, we actually called this p theta in the Ries-Thorn theorem, but oops. Yeah. So here p theta is just p. Okay. So right. So one of the problems with the Marcinkeiwicz interpolation theorem is that when P0 is close to P1, well, that forces P to be close to both of them, and hence both of these blow up. You do know exactly the rate of blow up. It's you know, basically like, well, 1 over P0 minus P1, essentially. But yeah, the fact that these two blow up when P0 is close to P1 is problematic, whereas for the Ries-Thorn theorem, you don't have any issues like that at all. There is no blow-up constants here. Okay, so in that sense, Ries-Thorn is better. Ries-Thorn is also better in the sense that you can basically pick arbitrary P0, P1, Q0, Q1, and as long as there's a theta between 0 and 1, where 1 over p theta and 1 over q theta are these numbers here, and as long as you practically have t is bounded from LQ0, sorry, from LP0 to LQ0, and bounded from LP1 to LQ1, practically speaking, then you have this nice bound here. From t is bounded from LP theta to LQ theta. And you need the flexibility, for example, proving Hausdorff-Young inequality. You absolutely need in Hausdorff-Young, you need the flexibility to not necessarily have P0 is Q0. So let's see what P0 is. Well, okay, in this case, P0 is Q0, but you know, you need P1 is not equal to Q1 for Hausdorff-Young. In particular, P1 is 1, Q1 is infinity. It's as dramatically different as you could want. Okay, whereas there really is no such flexibility for Marcinkeiwicz interpolation theorem. You basically just have, there are no Q's. It's just 1 over P is theta over P0 plus 1 minus theta over P1. So again, Ries-Thorn is better than Marcinkeiwicz in that sense. On the other hand, as we noticed, weak type inequalities are much weaker, or they are weaker than strong type inequalities. So in a lot of instances, as I mentioned, you just don't know. There's no way to really directly prove that an operator is strong type anything. And so you just need to, you know, you need to prove weak type inequalities. And that's the exact case we're in for the Hilbert transform. You do have weak type 2, because you have strong, you know, the Hilbert transform is an isometry on L2. But what we'll prove, again, as I mentioned, is that the Hilbert transform is weak type 1, and hence it's bounded for all p between 1 and 2. And this, in the case of the Hilbert transform, it's actually not going to be bounded on L1. And I think we even showed, if we did, and we'll definitely show it, I think we've showed that it doesn't even map L1 into L1. You know, the Hilbert transform, you can cook up a function pretty straightforwardly where the Hilbert transform applied to that function is actually not an L1. I believe we actually did that a few videos ago. So certainly there is absolutely no chance on planet Earth that the Hilbert transform is strong type bounded on L1. So you absolutely cannot use Restorin. But yeah, it is weak type 1-1. We'll prove that. Not easily, but we'll prove it. So, you know, Marcinkeiwicz interpolation theorem is exactly what we need. So, yeah, two very nice interpolation theorems that are just different, but equally good. And I want to make one final comment. There is something called the off-diagonal Marcinkeiwicz interpolation theorem. A good resource for that, if you're curious, is a very nice book called by Lukos Graphikos. And it's classical Fourier analysis. We definitely have it in the library, SUNY Albany Library. So the author is Lukos Graphikos, pretty famous Greek mathematician. And so the off-diagonal Marcinkeiwicz interpolation theorem is basically the same thing, except with the flexibility that these two are not necessarily equal. Okay. Now things get a little funky because you don't get anything. You don't get exactly a. You don't get a Lebesgue space bound. You get a bound in terms of something called Lorentz spaces, which are, you know, a much more subtle, much more precise version of Lebesgue spaces. So it is a little bit arcane, this off-diagonal Marcinkeiwicz interpolation theorem. The vast majority of the times you either use Restorin or you use Marcinkeiwicz. And there are versions of Marcinkeiwicz interpolation theorem for other various function spaces. That's kind of fairly advanced. It's called, those various theorems or the techniques used to prove it are called real interpolation. But it's important stuff. Professor Bachanu has used such theorems, you know, generalizations of Marcinkeiwicz to prove some nice PDE results in terms of actually Lorentz spaces. So yeah, if that sounds interesting, and if you liked the proof technique of Marcinkeiwicz, definitely talk to Professor Bachanu. Of course, if you like PDEs. All right, well, hopefully this was informative. And next, we're going to talk about dyadic intervals. We're going to stick to the real line to speed things up a bit. No other reason, really. Yeah, we're going to talk about dyadic intervals and the maximal Hardy-Littlewood maximal function, Calderon-Zygmunt decomposition, and then put all the pieces together to prove the Hilbert transform is weak type 1-1, roughly speaking. And then afterwards, if we have any time, we'll see what we do. I doubt we'll have much of any time, but I mean, I'm okay with ending at proving the Hilbert transform is weak type 1-1. All right, well, so long, take care, and yeah, until next time.